Are there any questions so far about how we've worked through this example? Sorry? Does the top have to be 1?
Yeah.
You'll see that we can change that. There's an example I'll show you where we're going to do it slightly different. And by the way, when it comes to substitution, marking the quizzes from the other day, some people really don't, they need to practice this, let's just say. If you know that you're not sure about what you're doing when it comes to substitution, you do need to see me. That's like our biggest technique. If you can't do the substitutions, there's going to be problems for the rest of this, until the rest of the course is over. So if you're one of those people, come see me at lunch, come see me after school, I'm around. We need to learn how to do this because it's like our biggest technique so far, okay? This is the end of the techniques today, by the way. We start talking about applications and things later. Okay, so then when we go down to take a look at, again, it's not obvious if you haven't practiced, that's why I've given you some hints. So we have to look at this and figure out which in the pattern does it most look like. If we were to look, I'm telling you this is inverse trig, right? You need more experience to say, oh, I recognize this. I'm telling you it's inverse trig. Which one do you think the pattern applies to? Yeah, it's arctangent because there's no square root in it. So what I'm going to do is I'm going to rewrite this, and I have to think about the arctangent pattern. So it's going to be a number squared plus some function squared. Okay? So in order to do that, really what I'm looking for is, you can think about it like this. It's like root 2 squared plus 3x squared. So this is the way we would think of this if we were to plug this in for the arctangent. Now, however, we can't just jump in and do it this way because we're no longer working with just something squared. It's more than just something squared. It's 3 times x, and then that all gets squared. There's a 9x now. How do we account for it? Well, the easiest answer is just to tell you that we can make a substitution. So I'm going to go to another slide because I'm running out of space here. But if we were to do it with substitution, I'll write down that last one. We say it looks like the arctangent pattern. I'm going to make my substitution, let u be equal to 3x. That means du is 3 dx's. So right away I can see that I need a 3 in order to balance this out, which means I need a 1/3 in the front. And now I can make my substitutions. 1/3 the integral of 1 over root 2 squared plus u squared, and I'm in terms of u now. Okay? So now that I've done it this way, there's no more worries as to, well, what do I do now that it's 3x squared? Oh, sorry, yes. Oh, no, there's no 3 on the top. That's a good question. The reason that 3 disappeared is that was replaced with the du.
Oh.
Right? Yeah.
Can you just write it in terms of x instead of u? Can we also do that?
I'll take that question in a second, okay? I want to step through this one first. There is a danger to doing that, and I'll show you how that works. So we go through this like we would substitution, and we go, okay, this is fairly simple now. My values are going to be, well, my function is just u, and my constant is root 2. So let's figure out, well, we said which pattern this was, right? It was arctangent. Okay. So here's the pattern that I'm going to have to fit it into. This time I'm working here. Okay. So it's going to be 1 over the constant. I think I'm here. Yes. So it's going to be 1 over my constant, and I've got a 1/3 in the front as well still, so I better keep track of that, times the arctangent, and it's going to be u over root 2. So our substitution was that u equaled 3x. My final answer would be 1 over 3 root 2. arctangent of 3x over root 2 plus a constant. Now, let me just show you why you actually do need to go this far and do the substitution. You can make a real careless mistake, and it's not an obvious mistake either. So let me show you. This, in fact, would be the correct answer for this question. Okay, now let me show you what happens if we try and shortcut things. It's very tempting for people to go like this and say, I've got 1 over, what do we say, root 2 squared plus 3x squared dx. And it's very tempting for us to just say, well, that means my function is 3x, my constant is root 2, so my answer is going to be 1 over root 2 arc tan 3x over root 2 plus a constant. What's missing this time? Yes? The 1/3 is missing. How come it's not there this time? Well, we didn't make that substitution, right? This is not a function here that would translate evenly. It does not equal dx. It would be, we found that it was 3 dx's. So this added 3, it's not an obvious mistake you've made, but you forgot that 1/3 if you just jumped right into it. So my advice is substitution is something you should be very familiar with. It's our go-to technique. We're still using it lots, so why not keep going with it? Okay, there's no need to rush that kind of question. So I'm going to have you try this one, and I've given you the hint again that use u equal to 2x for your substitution. Your first job is, which one does this match in the pattern? Once I figure that out, see if you can make the appropriate substitution and find its antiderivative. Okay, so you may need a couple minutes, that's fine. I'm just going to try and catch up to where you're at. So one key thing that we've just mentioned the first time is you've got to be able to recognize something squared. So I usually start by rewriting it so that I know what values I'm actually talking about here. So 2x, that would be my substitution right here, and my constant is going to be 3. But before I can do that, I need to make the substitution. So I'm going to say let u be equal to 2x. du is 2 dx's. So if I'm going to put a 2 in front here, that means I need a half to balance out. And let's see here where this takes me. So I'm going to have 1/2. This integral here is going to become 2 or du. And I've still got an x. And let's see here, that'll be u squared minus 3 squared. I can leave it like that, why not? And we could make our change for x, but it makes sense to move this fraction back into the integral, because then that will connect this up as 2x. So that means I'd be able to rewrite this as du over 2x root u squared minus 3 squared. And the reason that's helpful is that's equal to u from the substitution I made. So now I have an integral that looks like this. Okay. And that integral is the one I'm going to have to look for my pattern. Most of you probably figured it out before you started. What pattern are we working with now? Yeah, the arc secant. So this is the arc secant pattern. It's the only one that multiplies in the front like that. So if I was to use the arc secant, well, I just have u, and my constant is a 3. So here's the pattern for you, arc secant. Very similar to the arctangent pattern. So if you can get the arctangent pattern, it's almost the same to use arc secant. So this time I'm going to have 1/3 the arc secant of the absolute value for u over 3 plus a constant. And the substitution I made is up here. I said let u be equal to 2x. So I've got 1/3 the arc secant of 2x over 3 plus a constant. Okay. So can I just see how many people got this far and they were able to find? Oh, good. That's good news. This is usually a well, let's just say it's a messy topic, right? It's a messy one to find the antiderivative for. All right. This one is in disguise. This, in fact, is an inverse trig. It's a good exercise. Is it a fair question? Maybe. Again, if you're looking for arc sine, arc cosine, things like that, you're trying to find two things which have been squared. So one hint, if you couldn't figure out a way to do this, I don't know, maybe some of you would see the square root here and think, oh, maybe I'll look at my inverse trig rules. This is the way you want to think of this question. This is like dx over, I'm always looking for something squared. So what have I squared? It's e to the x that I've squared. Okay, so the hint here is your substitution is going to be for e to the x. And I'm telling you, this one, you got to kind of walk through it now that I've given you some major hints, because it's not obvious that this is going to work out, but it will if you use that substitution. So take a deep breath, look at your neighbor's paper, say, I believe in you, we can do this, and I'll give you a couple of minutes while you work it out. Okay, well, let's see how we did. I'm going to transfer this again to a bigger slide. So what we came up with so far is we're looking at dx over root e to the x squared minus 1 squared. So can anybody think possibly, like, it is an inverse trig. You may not, notice it with the amount of experience you've had now, but can anybody look ahead and kind of maybe guess which one this would fit under? Sine? Secant? Oh, there's some distension here. Let's, yeah, if this was going to be sine, it would be the constant. If this was a sine pattern, it would be 1 minus e to the x, and everybody would be squared. So it's not sine, not the arc sine. So, is it close to anything else up there? Possibly secant. So let's, as I say, take a deep breath and we'll see where this takes us. So if we were just to say that's the best we can do for now and make a substitution, then du is e to the x dx. So here's the thing, I don't have an e to the x, I'm short. But what I can do is I could put 1 at the top and 1 at the bottom. Now, yeah, oh. So now the advantage is this is going to turn and fit the pattern perfectly for arc secant. So let's keep going with this. I'll now have the integral of du over u root u squared minus 1. So at this point, I can go right into my arc secant. So that's going to be 1 over 1 is my constant. Arc secant, absolute value of u over 1. So this would be arc secant of e to the x. And of course, we can even simplify that a little more. What we could do is get rid of those absolute value sign, because e to the x is always positive. So that would be the best answer we could offer for this question. So the last thing I want us to talk about, I did mention this is our last technique in the unit. So what we have to be able to do is we have to be able to think about which strategy we could employ here. Now I got these examples from your textbook because they're pretty good at illustrating. They can look very similar yet use a different technique. But one thing I didn't like about these examples and found out, I guess the hard way, there were some struggles in the first block, which was how on earth do we do these ones? Well, this one I can show you, but this one is not possible by a method that we'd be capable of doing. So I'm just going to put these ones to rest because I don't like those kind of questions where they say, find the antiderivative. Haha, there wasn't one. Right? That's not a good thing to do to you. So we would just say not possible with our techniques. If we did have to work with this, we would do a numerical integration like trapezoid rule or Simpson's rule or something like that. I will show you this one later. It may be of interest to some of you at the end of the lesson. It's definitely somewhere some of you are going to be headed. Grade 11 students, if you're going to be going on to take Calculus BC, this requires, there's some work from Calculus BC in here. But it's not so far ahead that you guys wouldn't understand it. So I'll do this one last. But let's ignore those two for now. Yet another reason to kick your textbook? Drop it down the stairs? Or anyways, so we're just going to look at these four. And for example, in the first two, they look very similar. There's just slight differences. But what technique would you use? So what do you think? In the first one, we've got techniques like substitution, inverse trig, natural log. What do you think?
Inverse trig.
Yeah, that one looks like inverse trig to me. Which one would you recognize this as? Good. What about the next one? Good. It doesn't fit the pattern for arcsecant anymore, but what we would say is this here is going to be my function, and then you might say to yourself, oh, well, if I put a 2 here and a half in front, then I've got a function plus its derivative, so this would fit the pattern nicely for substitution. Okay. All right. What about the next ones here with natural logs and things? Okay, well, let's take a look. What about this first one? What will we do here? You have those three techniques. You have substitution, you have natural logs, and today we've been talking about inverse trig. What do you think? Well, let's rewrite this and figure it out. So there is a bit of a disagreement in our otherwise amicable class. So, does that change anybody's opinion? How about if I rewrote it like this? Does that help? Can I ask again, what technique would you use? Oh, it's still a division here. This is going to become a natural log question. So why is it going to be a natural log question? Well, you can't power rule that. You can't go from -1 to a function 1 higher than that because you would end up at 0 and this would cancel out. So this is going to become natural log. It's actually, we could do it really quickly. This would be the function. This would be its derivative. So it would be the natural log of the natural log of x. But anyways, remember that's another thing you got to be aware of. You can't power rule from -1 up to 0. That won't work. All right, and what about this last one here? What would you use? Okay, so what do you think for this last one? We could do substitution. We don't even have to get that complicated. Jackie, you want to? Well, let's take a look if we separate this. I see a function and a derivative, but I don't see a function with exponent -1. So if this is my function, and this was my derivative, then this would not work out as natural log because the exponent is 1. It's not -2. Or sorry, it's not -1. So what technique could I use here? It's a real simple one. Yeah, the power rule in reverse. So the power rule for integration. Because I've got a function and I've got its derivative, there's no need to substitute. It's not going to get really much different. You could substitute. You could say let u be equal natural log of x, then du equals 1 over x dx. So that could still rescue u, but if you can do this by matching up the pattern, some of you should be at the level now where you can see it and go, oh yeah, there it is, right? So substitution is always a good one to go to if you get stuck, but that one I think we could just call it a power rule question. Okay, so that's probably most likely what we'd say. So I'm going to give you the option at this point. That is accurate for your homework there. But I'm going to show you on a slide how to find the antiderivative for natural log. So if at this point you've had enough and you want to start working on your homework, that's totally up to you. If you're curious how do you find the antiderivative for natural log, I'll show you how that works. Okay, so the first thing you would need to know about another technique we haven't talked about is if this is true, that the derivative of two functions, f of x and g of x, is equal to this, does it make you, when you look all the way back, does it make you feel like, oh, I remember that, that was so easy, now it's, no, it's still, it was hard then, it's still hard now? Well, product rule, if this is true, then if we integrate both sides, this can help us figure out how to recognize the product rule in reverse. So if we integrated both sides, the integral of a derivative, what's going to happen to that? Or maybe I should say the antiderivative of a derivative. It cancels out, right? So it's just going to be back to this. So we're going to have f of x, g of x. But these pieces, it's not as simple. I'm still going to have these pieces like this. And you might say, now why on earth would you want to go from one thing to two integrals? Well, usually the way this is done is I'm going to rearrange this. So instead what I'm going to say is that means the integral for f prime of x, g of x, could be rewritten, and I get one integral for free. It could be rewritten as f of x, g of x, take away the integral for f of x, g prime of x. So you get one integral for free, and you end up with a new integral here for the one that you've started with. So the reason this technique can be useful is you end up differentiating. So for example, g, because I've differentiated it, you may have a problem that you can't integrate, and let's say it had an x squared into it. Well, the new integral, if you can't integrate it, would have a 2x. The next integral would only have a 2, and then maybe you'd have it beat, right? So it may take you several steps to get there, but this technique can knock down the integral so that you end up with something to work with. But anyway, this is the idea that you use to figure out the natural log's antiderivative. And what I'm going to do is I'm going to write the integral for the natural log x in a very clever way, which was not my idea, but it's so simple and yet so clever, it's very deceptive. There, brilliant, hey? Why would you want to do that? Well, again, if you look at your choices, one of them is going to be integrated from f prime to f. The other is going to be differentiated from g to g prime. So it's easy to integrate one. It's easy to differentiate natural log. That's why the person that figured out the first time would have made those choices. So just so you can see it easier, I'm saying let f of x be equal to 1 and g of x be equal, f prime of x equal to 1 and g of x equal to the natural log of x. So if I then fill it into the pieces that are over here, then on this side of the equation what I get is the integral of 1 times the natural log x is equal to, so I got to integrate 1, which is easy, that's just x, times the function I had, g of x, take away, take away the integral, which is x, and the derivative for natural log, which is 1 over x. So the new integral that I get is easier to work with. It's going to be the integral of 1, since those would disappear, dx. So I get x natural log x, take away x, plus a constant. So that is in fact the antiderivative for the natural log. You can verify it by taking its derivative. It will get you back to natural log. But it's a technique you probably would never have thought of, working backwards from the product rule. But it is possible. So for those of you who are thinking of the next course, maybe in university in second semester, or Calculus BC if you're going to take that, that's a topic in that course.